Hello everyone, my name is Chen Ankai from the IP department. Today I'm going to introduce my graduation project, FIAS. We basically wanted to build an LLM fitness coach, a real-time fitness coach for anytime, to do anytime, anywhere. So actually the motivation, it's like when we're doing COVID, when you're at home, like you cannot, like there's no one to guide you to do when you're doing exercise. So basically we wanted to make like a system where user can input a video or even like real-time video to give you real-time feedback, and at the end will generate kind of like an LLM report like this. So in any deep learning project, the data set is very important. So when we're doing like survey, we see data set that has big categories, like it has squats or push-up or lunge, but doesn't have fine-grained details. That's why we create our own data set with approximately around 2,000 videos. And also, the existing data set didn't explore like how different camera angles or how camera angles or viewpoint will affect the model's performance. That's why when we're creating this data set, we make sure to have some front data and back data, and the performance we can see in the key results later. But I want to introduce our performance, the framework, the pipeline of our model. So for human action recognition, usually we use the skeleton data instead of RGB frame as an input. This gives the model a better understanding of how the human joints interact with each other. And we use a deep learning model called SDGCN. Basically, the S stands for spatial, so it learns the characteristic with the different key points the relationship of key points within a single frame. And the T means temporal, so it analyzes how the movement or how the key points changes with time. So after this deep learning model, it learns how to generate the correct class. The correct class is just what motion the things it predicts. So it could be squat mixing or a squat feet to toes. But deep learning model has a problem, like we don't know how it gets that answer. So we implement something called a GradCam to see how the model predicts this class. So it analyzes the activation heat map, and for example, when I'm doing a squat, like initially you can see it is more like blue and green on all key points, and when I'm doing squats, the model focuses more on the knees or the ankle joints, so we can know how the model focuses throughout the motion. And this is very important since we want to create a fitness coach. We need to give more than just action class to the LLM to create a better prompt for LLM to reason. So here is our key findings. As I mentioned before, we created data set with different viewpoints, and in our testing within our own data distribution, the first thing you can notice is 2D model performs better than a 3D model. The second thing is you might think a model that trains on the front view also performs the best at the front view. But interestingly, the model that trained on both viewpoints actually perform best when it's being tested on our front data. So that means like the model when it has more diverse viewpoints, it doesn't just only learn to generalize to different viewpoints, but it learns a better representation of the human motion itself. Since it's a real-time system, we also analyzes the real-time metrics, and we realize that the model is not that good when it's differentiating like fine-grained details, but we only analyze when it's doing either like the bigger categories, it reaches almost 0.5 NIOU, which is like a decent amount for a real-time system already. But since we want the model to be better at fine-grained detail, so we added some custom augmentation to boost the model's accuracy, and it increases within our own data distribution from 0.95 up to 0.99. So in conclusion, in summary, like 2D with a better diverse data and augmentation, we can get a better model rather than using 3D dimensionality. Thank you.
Thank you for your presentation. Just a little question. How do you detect the point of the joint, the place of the joint? Is that you put the sensor here or you would just detect?
There's a model called RTM pose. It can basically, if you input the model, the model can tell you where's the key points on the frame. So this is like a deep learning model that someone already trained, and it's very good at detecting human key points. So we just use our model to get the key points and use it in our training deep learning model.
Because for me, I have done this kind of experiment before, so it's like when you detect the points, the joint points a little bit differently, then the result will be different. So I just wonder how the accuracy, how it accurately detect the point of joint. And is that always consistent when it always, detect the same points? Have you done this kind of experiment to make sure that the measurement is always consistent?
So basically, we didn't do like a quantitative one, we just see qualitatively, and the model, I think the model did a pretty decent job already, but we didn't, because this is not our experiment, it's not what our experiment is focusing on. There's more in-depth research on how to make a better key point pose estimation model, but this is not our focus.
Okay, I think a good coach should not only require the accurate, but should also need to know the capability of the person. You check the pulse, you should check the heart rate to see. You should also see the visual. Is it visibly in pain? Then you shouldn't sort of push, right? You shouldn't just to do it accurate. That probably is already too much. You said you should lessen that, right? You shouldn't just insist on accuracy.
That is true. But for now, our model doesn't.
We should have a feedback and see. You can do it. You can loosen it up because you're already in pain.
I think that's a good feedback. I think maybe in the future.
Okay, great. Thank you.
Thank you.